right, so any questions?
Why do certain birds not fly while other ones do?
Yeah, that's a good question. And where do you get a white snowboard?
You don't get one, you earn one.
You earn one, that's right. Good answer. All right, so good on decision trees, PA4, all that sort of stuff. Good enough. All right, so let's talk about threads. So in C, we talked a little bit about forks. And you could have a main program and you could call fork, and fork would create a clone of your current process, and the return value from fork would be different between the original process and the clone process, right? The clone would get back a 0, the original or parent would get back the process ID of the clone. And then it's up to the code to go off and differentiate based on that return value or something else. And that works reasonably well, but it's fairly C-like. So Java has a mechanism for doing something similar. So the main thing we're talking about are threads. And thread is a class, okay, like everything else in Java. And it descends from object. And it's got a variety of methods. We can get the ID of a thread. We can look at a stack trace, a list of who called who in the thread. We used to be able to do things like destroy and stop and suspend and resume, and those are deprecated because they're considered unsafe to use in terms of deadlock, right? Because destroying a thread that's got access to a resource that another thread needs, destroy doesn't do any cleanup. It just kills the thread, and now this resource is locked by a non-existent process, and it never gets freed. And you've got a good prescription for deadlock. So some controversy around this, lots of discussion, but in the end, these things are deprecated. So we have to deal with thread management differently. The main thing we're interested in with threads is this thing called run. It's a method. Public void takes no arguments. And run is just a method, right? Doesn't really do a whole lot by itself, but there is this method called start. And if you call start on a thread, what it does is it creates a new thread, right? A new execution process, context, and it looks for a method named run inside that thread and starts executing it in that separate thread. So start does two things, creates a new thread and then executes the run method. Right? Run by itself is just a method. Nothing special about it. All right, so I'm going to put all of my classes inside one file, just so we don't have to keep switching back and forth between windows. So our goal is to start off our public static void main string bracket bracket, right? Starts executing. At some point, it's going to create a new thread and cause that to start executing. And it should be executing at the same time that our main thread is also executing. So to do this, we can define a class. And we can say that our class extends threads. So this is like when we extend a J-frame. We're absorbing everything that's in the thread class, and that's now part of the myThread class. But we can also add new methods, and we can override methods that are already existing. So let's do the following. All right, so all I've got in my thread class is, in my mythread class, is a run method. And it's just going to loop 100 times and print out consecutive integers. And we'll go ahead and do a print line at the end. So our main method is going to construct an object of type new thread, my thread. And if we call the run method, it's just going to run this loop. And no big surprises there, right? Okay, so let's put a similar loop in here. And let's print out where main is starting. Let's go through a loop and print out 100 integers from main, and then we'll say main is done. So let's just see what's going on in here. So we'll print a message when main starts, we'll print out 100 integers, and then we'll say main is done. We're going to call mt.run, print out run is starting, print out when run is done. So this is not going to be terribly interesting. It said run is starting, printed out 100 integers, said run is done, and then it said main is starting, printed 100 integers, said main is done. Okay, because what did I do? I called the run method in my thread, and that comes down to run, says run is starting, prints 100 inch, says run is done. And then it comes back to my call to run and starts the next line of code, which says main is starting. Okay, single thread, right? I just called a method. But if I call this method named start, that's going to do something totally different. That's going to say create a second thread and execute the run method in that second thread. And now we're going to have two threads executing at once, and this is going to be completely different and possibly shocking. So it said main is starting, it said run is starting, and we see 0, 0, 1, 1, 2, 2, 3, 3, right? So they're each outputting a consecutive integer, and then someone did 4, 5, 6, and then someone did their 4, and then 7, and then one of the processes took over completely. It looks like run, went all the way up to 99, then said run is done, and then main came back at 8 and finished up. So this is asynchronous, right? These are two things with their own sort of execution contexts. And what's even more fun / horrifying, if I do this again, totally different behavior, right? This time main finished first. And if I do it again, totally different behavior. This time run got almost all the attention. There's a single output from main right here. And other than that 1, 0, right, this was all the output from run, and then main finally came in and started and finished up. Okay, and this is a feature, not a bug, because we want these things to be executing independently. If we want them to do things in some sort of synchronized way, it's our responsibility to synchronize them. And there's different ways that we can do that, but one way is shared memory. Because we're constructing this thread, right? My thread mt equals new my thread, which means that main, the thread that's executing main, has access to the thread that's executing this run method, right? Just through mt. But this thread mt has no idea where it came from. So here's something we could do. We could make I public and make it a class variable in my thread. and we could do the following. Well, mt.I is less than 50. I don't know if we need bracket there. So we could have the main thread wait until the MT thread's I reaches 50, and then it can say main is starting. And I don't know if I need bracket after that while loop. Nope. Alright, so run is starting, and oh, that didn't work. Let's see. Backpedaling quickly. Interesting. I gotta think about that. I don't think this will make a difference. Yeah. Maybe I did need a bracket. Nope. Alright, well, I'll have to play with this over the weekend. Something goofy going on here. But anyway, I have a theory. I think the thread is exiting and I isn't available. But anyway, so we can share memory, okay? I think it's going wonky because this thread is exiting at the end. Okay, I'll play with it later. So we can pass information back and forth, even though it looks like we can't right now, to synchronize these things. But the point I was heading towards is, because these things are inherently asynchronous, right, debugging them can be kind of tricky, right? Sort of like what we're doing here. Because you might have code that works great 4 times out of 5, and then the 5th time you run it, it doesn't work. You can't necessarily reproduce those conditions under which it failed. And it may just be that when you run it 100 times, it fails 6 times, right? And this makes it hard because you can't necessarily force it to fail, and you can't go through it in a debugger or something in a way that you know is going to fail. And in fact, with threaded code, a lot of times it's going to work fine in a debugger because things will happen more slowly and they'll be separated out and you'll be stepping one step at a time. So it's notoriously tricky to debug multi-threaded stuff, but that's part of what makes it fun too, right? Because there's all these weird behaviors, kind of like this. All right, so we can also, I'm going to save this, the French bug. So let's get rid of all of this. Alright, so here we're going to start my thread, and then it's going to say main is done, and then it's going to go ahead and execute the loop of 100 outputs in my thread. Oh. Alright, so what's the point here? Main exited before run even started putting any output out. Right, so your main thread doesn't have to stick around. Right, it can start doing something, it can create a new thread, and this might die really quickly. And in general, when we do swing in Eclipse, the way it sets things up, your main method exits right away. And swing is working because there's other threads in the background that are doing things like waiting for events and notifying listeners of events and so on and so forth. So we can do multiple threads. So there's 5 threads, and who knows what order they're operating in. Now we can't pass arguments to the run method because the signature changes and it becomes a different method. It's not the thing that gets called by start. But when we construct, we can certainly pass information. So I'll pass an ID to my thread class. So now when I construct, I'll pass an integer and it'll save that in a class variable named myID, and when I output I, I'll put my ID next to it. Alright, so here you can see better where things are being run at the same time, and in the beginning up here we've got a pretty good mix of job 1, job 3, job 5, job 4, and so on. And again, it'll change from run to run. Alright, so why do we care about this? Why do we need threads other than for making goofy random looking outputs? There's a model of organizing processors called the client-server model. So a client-server model is a really common setup where you have a server, typically a process, that is basically taking requests from somewhere, processing those requests, and typically sending back information as a result. Okay, so a classic example would be a time server. So a time server you connect to, and you don't actually give it any information, it just spits out the time, right? And you can use this to synchronize the clock on your laptop, for example. So you contact the server, it just sends you some information, and you're done, okay? The client is the processor, program, or entity that's making the connection to the server. The server is the entity that's taking requests and supplying information. It's not a totally rigid definition because sometimes both ends of this communication are taking requests and supplying information. But usually servers are kind of pre-existing. They're sitting somewhere on a system and they're constantly running and they're waiting for these requests, and clients kind of come and go. Okay, so a pretty classic example of this would be an SSH server. So SSH is the way that you communicate securely between something like your computer and Linux engrcs.com. And so SSH server, SSHD, is a process sitting on Linux engrcs.com that's waiting for connection requests. And when you run PuTTY or you say SSH or you use whatever your favorite client software is, it basically makes a request to the server and says, hey, I'd like to log somebody in, here's my username, here's my password, and it authenticates, and if you're successfully authenticated, it starts a separate session, runs bash, and connects your input to the input of bash, and standard out of bash goes to your output side. There's print servers, right? So you have a machine with multiple people using it, you have a single printer hooked up. You can't have each person who wants to print something talking directly to the printer, because printers take long, complex commands that tell them how to format, when to feed paper out, and so on. And if two people start sending commands to a printer simultaneously and those commands get mixed together, it's gibberish. So you have a single process on your system, which is called a print server. And the print server's job is to send commands to the printer, and it's the only process out there that's talking to the printer. But when you want to print something, you run basically a client program that takes your print request and sends it to the print server. And if the print server is already dealing with another print job, it will queue your job up, and when the printer is free, it'll take the file that you sent it and it'll spool it out to the printer, right? It's a client server setup. And these are threads, right? When you want to send something to the printer, you don't want to have to sit here and wait until your job actually prints. You want to make the request and go on with your life, right? So you might have a separate thread running that's making that request, doing the communication with the server, and your main thread can continue doing whatever it's doing. Okay, so here's a client-server model we're probably going to encounter for PA5. So picture a chat program, and we have a client, and we have a server. And this is a model where, as I said, sometimes it breaks down because both sides are going to be sending information and receiving information. But we can think of the server as kind of like a help desk. They're always available to talk, and the client is someone who comes along and says, hey, I'd like to talk to the help desk. And so they initiate a connection over here. And in C, we can open files, right? And we have this file pointer, and we can write from there, we can read from there, and so on and so forth. And when you write into a file, it goes into the disk, and when you read from a file, it reads things off of the disk, right? We talked about pipes in Unix, and a pipe is kind of like a file, but instead of sitting on your disk, it's like this sort of virtual file. And I can open one end of the pipe, and another process can open the other end, and if I write into this end, the other process can read what I wrote. Okay, so that's a pipe, and that's how you connect commands together with the pipe symbol. There's another level of this which is called a socket, and I can create a socket over here, and you can create a socket over here, and they can be connected through the internet or any other network. And if I write something into this socket, you can read it from your socket, even though I'm in room 156 and you're on the space station, right? So it's like a network-based pipe. So we're going to talk about sockets next week in here in Java. But here's something we can do with them. We can make a chat program, right? So pseudocode for this, pretty straightforward at a first level. Client can do the following: read from standard in. So let the user type in a message. Send whatever they typed in to the socket, right, to the server. And then read from the server. and send to standard out. And go back and do it again. And on the server side, same thing. Read from the client, send to standard out, read from standard in, and send to the client. Go back up. So at first this works great. Client initiates a connection, says hello there, right? Program reads from standard in, reads hello there, sends it to the server. And the server was waiting to read from the client, so it reads hello there, sends it to standard out. Now the person on the server side sees what the person typed on the client side, which is hello there. And the server says hello back, reads from standard in, sends that to the client. The client, meanwhile, was trying to read from the server. It reads hello back, prints that out. Now you're both typing and seeing what each other's typing. Okay, that's pretty straightforward to implement once you know how to do sockets, but there's a fundamental problem with this pseudocode. So what's the problem with the algorithm?
These have something to do with their like sending stuff at the same time.
It's related to that.
Like one's sending, one's reading.
Mm-hmm. They're always waiting for each other. So this works great the way I described it. What if this person wants to send 3 messages to the server? They type in their first message, hit enter, that gets sent to the server. They're sitting here, they're waiting to read something from the server. They can type their second message and hit enter, but it's not going to get used until they read from the server, display what the server sent, come back up here to where they read from standard in. So they can send one thing, but they can't send anything else until the server sends something. And then the server gets read over here. The server can't send anything else until the client reads from the server and sends something else. So they're working in lockstep. One message, one message, one message, one message, right? And that's just kind of goofy for a chat program. Well, maybe there's a place for that. Maybe it would make chat more equitable. But an easy fix for this is to make a pair of threads. Have one thread whose whole job on the client side is to read from the keyboard and send to the server. Read from the keyboard, send to the server, read from the keyboard, send to the server. Simultaneously, a second thread is running on the client side. Read from the server, send to the display. Right? And now if I type in 15 lines and send them to the server, right, this loop just keeps running through and through, and this just happens to be sitting here waiting to read from the server. When the server finally sends something, this thread will go ahead and read it and display it, but it doesn't interfere with this thread's reading from my keyboard and sending to the server, and the same thing on the server side. So that's where we're going to end up using threads in PA5. And we're going to end up with at least 4 threads, possibly more. All right, this is also useful when we're doing things like graphical output. Because in Swing, when we want to paint on our window, what do? We put some code inside the paint method that we've overridden, and then we call repaint when we want it to update the display. And repaint doesn't actually go and run paint, it simply logs a request and says, when you have a chance, call the paint method. But if we make a for loop or a while loop that runs forever in our main method that updates some information for the paint method and then calls repaint and updates some information and calls repaint and so on, and that loop never exits, we're never going to see those painting events, right? Because we're never giving Swing a chance to do its thing and to say, hey, I should go ahead and call paint. And so we would typically do these things that are running in this forever loop to update the information for painting, we would typically do that in a separate thread. And periodically we can say, hey, go ahead and take a break, let other threads have a turn, and that's when Swing can come in and go ahead and do its repaint. So I'll dig up some Towers of Hanoi code for Monday that does a graphical version of Towers of Hanoi. We've already done the code in 2.15, but we'll see how to do that on in Java with Swing, and we'll have to use a thread in there. All right, so this is one way to make threads, is by extending the thread class. And this is really easy to use, right? Just define your class, say it extends thread, and then just override the run method. And then to actually kick it off, just call the start method, and you've got a separate thread. There's one problem with doing this, which is Java will only allow you to extend one class. You can't extend multiple classes. Some languages will let you do that. Java does not. So if class myThread extends thread, I'm done. If I wanted myThread to also extend a JFrame, I can't do that. And sometimes that's a problem. So there's a totally separate mechanism we can use that'll allow us to create a thread and run something in a separate thread without having to extend the thread class. And this gets into some other machinery of Java that I'm not going to harp on, but it's not bad to touch on for a Wednesday afternoon. So, so the topic here is interfaces and implements, and in some sense abstract. And we've used the first and third word here before when talking about data structures. Right? When we talk about stacks, we talk about stacks as an abstract data type, and we talk about the interface between the user and the actual stack code. And the actual stack code is, I don't know, making a linked list and pushing things in the beginning or popping them from the beginning, right? But the user's interface to that is something called push, something called pop, something called isFull, something called isEmpty, and that's it. And then there's all this other stuff under the hood that's churning along to do what you need. Okay, so Java has support for these ideas of creating an interface to something. And so let's just do some code. So let's make an interface. So what is an interface, roughly speaking? It's a description of what a class should contain. Okay, it's not a full class in itself, but it's kind of like a blueprint for a class. So suppose we were dealing with lots of shapes, circles and squares, well, maybe not circles, squares and rectangles and triangles and hexagons and all these other shapes, right? And this is a really useful set of classes, and we realize that other people might want to create shape classes of their own, right? Maybe we never made a 173-sided shape class, and maybe somebody really wants to do that because that's what they do in their village, right? So it would be nice if they could use our model for what a shape class could look like and not have to reinvent the wheel from scratch. And so an interface will let us describe basically the structure of a class and also write some default pieces of code. So let's just make some silly examples. Interface, and I tried to figure out earlier how to do this with shapes, and I can't come up with a good example. So we'll just go with something silly. So we'll just make an interface called, we'll call it some interface. And this can define signatures for different methods. So I can say there's an abstract method. It's always going to be public, right? So there's an abstract void method called, I don't know, do stuff. and it expects, let's pass it one integer, and it returns nothing. And we're not saying in here what do stuff is going to do. We're just saying that if you're going to make something of this type, some interface, you're going to have a do stuff method that takes an integer. And maybe that's our whole interface. Okay, so now I want to make my own version of some interface. So I'm going to say class my interface implements some interface. Okay, let's see how many errors we get here. Typo. Okay, so I get one error here, which says my interface is not abstract and does not override the abstract method do stuff. Okay, my interface does not override do stuff. Because do stuff is declared to be abstract in some interface, it's saying you've got to write your own version of do stuff. Okay, it's required. So I can write that. So there's some useful stuff. And if I do stuff I, it's going to print out I squared equals and show me what the square of I is. Alright, so that'll compile fine. And so now I have my own class called my interface, right? Let me not call it my interface, let me call it my class. I have my own class called my class that is built on top of this interface. And I can use this like any other class. And I can call methods inside there, so I can call the do stuff method with a value of 22, and it tells me 22 squared. Okay, so why do we want to do this? This seems really heavy-handed, right? Because we can have default methods, so we can say default void do more stuff. And do more stuff just prints out doing default stuff. Alright, so I can say MC dot do more stuff. Okay, so this interface code is I put this in the wrong spot. This interface code is usually provided for you, or might be provided for you. Right, so the interface is usually not part of what we're writing, perhaps. We're just writing this, okay? So we're saying my class implements some interface and we're writing a do stuff method which prints out I squared. But when we construct an object of type my class, it's got a do stuff method, it's also got a do more stuff method, right? And the do more stuff method is some default behavior, which in this case just says doing default stuff. But if I wanted to do something more in particular, I can write my own. Right, so I've written my own version of do more stuff that'll do some really interesting stuff. And so when I run that, that's what do more stuff does now. And this is exactly what we get when we do class extensions, right? We get the ability to inherit, in some sense, a bunch of default behaviors, but we can also override some of these. right? But with interfaces, we also have the ability to force whoever is in some sense extending, but implementing this interface, we can force them to write particular methods and say you have to have this method in your class, right? So if you're trying to create an interface to some piece of hardware, for example, you may say you've got to have an initialize method, right? And we could set that up as abstract with no body, and they'd have to write that, but some of the other stuff we could just leave as default. So for us, for threads, the advantage is that this class that we write doesn't use the keyword extend, so it could still extend something else. So there's an interface called Runnable, and runnables are a way that we can get multiple threads going without having to extend the thread class. So our terminology is going to be, well, we'll just write some code. So we're going to say class myThread, and we're going to say implements Runnable. And so we're basically extending this Runnable. And we're going to write our own version of a run method. So public void run. Alright, so there's our whole myThread. And bottom line, looks like if we said class myThread extends thread, but we could extend something else. So we could extend a JFrame or whatever else we need. So we've got our run method, right? We've overridden that. And so how do we actually make this thing a thread? So, bless you. So we can create an object of type thread. So thread t equals new thread. Sorry, first make a runnable. So myThread mt equals new myThread. So same as usual, but now instead of just calling myThread.start, we need to create a thread, but we construct it with this runnable, right? So thread t equals new thread, constructed with the argument of mt, and then we can say mt.start. And that will create the second thread, and it'll call the run method in this class myThread. So slightly different, a little bit more work, but it's really not all that much work. We could just do this. Right, that works also. Because we don't need a separate object t. We're only using t so that we can call, sorry, this was t.start. We're only using t so we can call start. So we can just say construct a new thread with mt and then call the start method. And it's not terribly exciting because we only have one thread, but we could do it in multiple threads. All right, so two different ways to do threads in Java. So yeah, a lot more to say. So some of the things we can do in threads, we can interrupt threads. And when you interrupt a thread, it doesn't actually stop it, it just sets a flag somewhere that says I've been interrupted. But we can make a loop that, for example, checks to see if we've been interrupted. And when we are interrupted, it does something else. Typically it exits, but it might just do some other behavior. And anything that has access to a thread object can call that thread object's interrupt method. And that will signal an interrupt request. Okay, so back to 270. You can make a request and you may or may not respond to it, and how you respond to it is up to the code. So we'll play with interrupted on Friday. And what else do I need to tell you? There's a lot I want to tell you. We'll play with interrupted. And then Friday, I want to play around with how we can get into trouble with this stuff, because that's a Good Friday thing. So I want to look at some of the things that can happen if we don't pay attention to the interactions between these asynchronous threads. What kind of troubles can we get into? Some of them unexpected. And then we'll talk about how to deal with those and how to prevent them from happening. And then we'll spend probably a bit of time on, we're not meeting Monday, right? Okay, so this is a Good Friday exercise then. So Tuesday, we'll probably spend a little bit of time wrapping up some of this material. Yeah, we'll play with some more threads. And then probably Wednesday, we'll start talking about networking. And next week is week 8. So we'll spend at least a week on networking. Friday we'll go over PA5. PA5 you only have 1 week for, but it's a group project. So we'll get going on that Friday. And then a bunch of stuff to talk about week 9. We'll go through some web stuff and tie some of these things together. And then week 10 will probably be, project presentations and catching up on any last topics and reviewing for the final, and then we're kind of done. It's like a really fast spring. But okay, cool. All right, I will see you tomorrow. Tomorrow is open lab, so come if you want to do stuff in here. Otherwise, I will see you on Friday. I'm going to figure out why that example didn't work, because it's eating at my brain.